Hi guys, narrated solution number 2. Revolve the region bounded by y equals 4 minus x squared. Y equals 0, x equals 0, for x is greater than or equal to 0 about the y-axis. So we have this function being rotated about the y-axis. So if you're rotating a function about the y-axis, think about what your representative rectangle would look like. He would have to be horizontal. And if he is in fact horizontal, when he is swept out in order to generate a 3D solid, that slice is going to be horizontal. So if we took that slice and thought about it in terms of a radius with a height of dy, you will now notice that we are going to have to integrate with respect to y. If our delta y is now like that, we are going to have to integrate with respect to y. If you'll notice in the problem that we did earlier, we had a dx, we had a delta x and a dx. We had to integrate with respect to x. So now, since we are rotating about the y-axis, we are generating horizontal representative rectangles, and therefore we are going to have to integrate with respect to y. So let's go ahead and pause the video, copy down all of these pictures, and then we'll meet back in 2 seconds. Hello, welcome back. So since you may have seen already that we had an original function of y equals 4 minus x squared, but now our radius is going to be this generated by this function, the square root of 4 minus yi. Well, where did that come from? Well, we know that now if we are integrating with respect to y, we are going to want x in terms of y. So if we want x in terms of y, when you are rotating about the y-axis, you are going to have to solve the original function given for x. So when you solve the original function given for x, we start with y equals 4 minus x squared, and we're going to go ahead and solve for x. So we have 4 minus y, square root both sides, and we now have x is equal to the square root of 4 minus y. So when we have that, that is going to be the function that now generates our radius. So that's just where that little guy came from. So we're going to use that function to generate the radius of our representative disk, and we're going to use that to find the volume of each of these disks. So that way when we sum all these disks up, we can get a volume of the 3D solid. So I'm going to erase this because I'm going to need that space. And I'm going to go ahead and write the approximation of volume for my disk. So I have delta VI is equal to pi times the square root of 4 minus yi squared times the height of the disk. And the volume of the disk is thus going to be pi times the square root symbol is going to disappear, and we just have plain old 4 minus yi times delta y. So then now we have that as the volume of our disk, and we're going to take those disks and we're going to set up a Riemann sum to approximate the volume of this 3D solid. So now we would have the volume of pi times, if you'll notice, we factored the pi out front of the Riemann sum. We start with one disk and we head to n disks, and then our function here is going to be 4 minus yi times delta y. This is our Riemann sum approximating the volume of the 3D solid. Now let's let n head to infinity, and we are now going to get our integral, which is a continuous sum, and that is our definite volume. So an exact volume, in fact. So now we have our little integral here, and he's going to be volume is equal to pi. I factored the pi out front from 0 to 4 of 4 minus y dy. We are integrating with respect to y, so we would go ahead and get pi times 4y minus y squared over 2. And we are integrating from 0 to 4. We would get pi times 16 minus 8 minus 0. So we would get a volume of 8 pi or 25.1 units cubed.